These are the theorems for the Wronskian that we're going to discuss. So the first thing here, we have this nth order linear ordinary differential equation, homogeneous. So write the nth derivative of y plus some function p subscript n minus 1 of x times the n minus 1th derivative of y plus dot 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 all the derivatives in between plus p sub 1 of x with the first derivative of y prime, plus p sub 0 of x times y with no derivatives, 0 derivatives equals 0. And it's also part of an initial value problem, so we have y evaluated at x naught equals y naught. X naught and y naught are numbers. Y prime evaluated at x naught equals y naught prime. Y naught prime is a number, comma dot 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 for all the derivatives in between. Finally, the n minus 1th derivative of the function y evaluated at x naught equals some other number y naught with a superscript of n minus 1 to pair it with the n minus 1th derivative of y. And this x naught number we're using is in an interval I. All right, so we have the Wronskian of all the homogeneous solutions to this differential equation, y1, y2, comma, dot, 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 up to y sub n. If the Wronskian of all those does not equal 0 in an interval I, except at isolated points. So what I mean by that is, right, so if you evaluate the Wronskian, it's going to be pretty horrible if there's a lot of functions. It's a large determinant. But when you do finish evaluating it, it's just going to be a function of x. And so you can graph it. So here, let's say you have, x versus the Wronskian, and the Wronskian function comes out, the squiggly line is always positive. That's fine. Well, okay, what if you have the Wronskian versus x, and the Wronskian comes out as an exponential? So as x increases towards infinity, the Wronskian increases towards infinity. As x decreases towards negative infinity, the Wronskian asymptotes to 0, but it never equals 0. That's fine. You can have the Wronskian cross, though. So let's say the Wronskian is a parabola. So you start out positive. As x increases, eventually you cross the x-axis. The Wronskian becomes negative. Then x increases some more. You cross the x-axis again. The Wronskian becomes positive. Those 2 points are isolated points where the Wronskian is 0. So that's okay. So the Wronskian does not equal 0 in an interval I, except at isolated points. That implies these functions y1, y2, dot dot up to y sub n form a fundamental set of solutions in the interval I. And kind of equivalently is y1, y2, dot 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 up to y sub n are linearly independent in the interval I. All right, so the next bit is just a slight difference here. If the Wronskian does not equal 0 at x equals x naught, that implies the initial value problem can be solved. All right, so you can still have these linearly independent solutions. You can still have it cross the x-axis. They can still be linearly independent. But when you do cross the x-axis with the Wronskian, you may or may not have a solution to your initial value problem. And we'll see that in some examples. Another thing to note is reading the fine print here. If the Wronskian of all these functions equals 0 on an interval I, so not just isolated fixed points, that does not imply, with my big line through the imply symbol, that these functions y1, y2, dot 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 y sub n, that does not imply they are linearly dependent. And it's going to turn out, actually, there's an example where even the Wronskian is equal to 0, but the functions are linearly independent. But they can also be linearly dependent, so the theorem doesn't tell you anything when the Wronskian is 0 for an interval, not just isolated fixed points. These functions could be linearly independent, linearly dependent, and you'll need to investigate further.